In this video, we will be looking at trig ratios in radians. And a big focus of this video will be using special triangles, but again, in radians. A lot of the terminology, a lot of the skills will be familiar to grade 11, except instead of degrees, we're going to be working in radians. So before we get into that, just a little refresher on some terminology. When you have an angle in standard position, you have your initial arm on the positive x-axis, and you have your terminal arm that is swinging around the Cartesian grid. And wherever it stops, that's your terminal arm, and that is your angle in standard position. Now, you can read your angle as a positive angle or a negative angle depending on the direction the terminal arm moves in. So if we move counterclockwise, we have a positive angle. And if we were to move clockwise, we would have a negative angle. Now, this angle in standard position can be written as many different angles, and these are called coterminal angles. So they are angles that have the exact same standard position. The initial and the terminal arm are the same. The only difference is how many rotations apart those angles are. So if we just add or subtract a rotation, we'll get a coterminal angle, and we can do that however many times we want. So for this first example, we'll get a positive and a negative coterminal angle for each. So for 5 pi over 3, I know a full rotation is 2 pi, so I will add that on. Now, of course, I'm adding here with fractions, so I'm going to need a common denominator. 2 pi is technically over 1, so when we multiply top and bottom by 3, that's 6 pi over 3. And now when we add our numerators, 11 pi over 3. That is a coterminal angle. It will have the same standard position. And I'll do the same thing for a negative coterminal angle. I'm going to subtract 2 pi. Since I already got a common denominator in my previous calculation, I'll just subtract that common denominator. So subtracting that 6 pi over 3, and we get negative pi over 3. And I can add or subtract 2 pi however many times I want. So there are an infinite number of coterminal angles for any angle in standard position. For the next one, we have pi over 6. So me adding 2 pi, and I need a denominator of 6, I'll multiply 2 pi over 1 by 6, and that's going to be 12 pi over 6. 13 pi over 6 is a positive coterminal angle. A negative coterminal angle, so subtract 2 pi again, but in the common denominator form, and we have negative 11 pi over 6. I'm choosing to just add or subtract once, but again, you can do it as many times as you'd like. Last one, take a pause, try it on your own, come back and check with the video. So for your positive version, when you add 2 pi or 8 pi over 4, we get 5 pi over 4 as our positive coterminal. Our negative coterminal, when we subtract 2 pi or 8 pi over 4, we get negative 11 pi over 4. So there's some terminology coming back. Initial arm, terminal arm, that's standard position. Coterminal angles are angles that have identical standard positions. Now let's get to our special triangles. We saw 3 special triangles last year, and we'll begin with our isosceles right angle triangle. An isosceles right angle triangle, the 2 angles are both 45 degrees. 45 degrees is pi over 4. Okay, if we need a little refresher, we're taking 45 and multiplying it by pi over 180. And when we reduce the 45 over 180, we do get pi over 4 because 180 is divisible by 45. And now for the isosceles triangle, the equal sides are both 1, and if you did Pythagorean theorem, you would get root 2 for your hypotenuse. And in this special triangle, you only have one reference angle, either of the pi over 4s. So your opposite is 1, your adjacent is 1, your hypotenuse is root 2, no matter what. The other special triangle comes from an equilateral triangle that has been cut in half. An equilateral triangle has all three angles as 60 degrees, but 60 degrees in radians, if you multiply by pi over 180, is pi over 3. So that's our base angle. The top angle has been cut in half, so it should be a 30-degree angle, which again, if we multiply by pi over 180, that is pi over 6. Because the angles are different, either one can be used as a reference, but remember that 90-degree will never be used as a reference angle. Now the equal side in the equilateral triangle is 2. The base that has been cut in half is 1. And if you use Pythagorean theorem, you could always solve for that height to get root 3. So here we're going to use either pi over 3 or pi over 6 as our reference. So 3 potential angles so far. The last triangle isn't really a triangle. It's a fake triangle. So let's say this is my right angle here. This angle here is 90 degrees, which doesn't make sense to have two 90-degree angles in a triangle, because really that means you have two sides glued together. But I'm faking it as a triangle so that we can at least see an opposite adjacent hypotenuse. And 90, if we multiply it by pi over 180, is pi over 2. And the top angle will be 0. Now notice I did label this with the right angle notation because I'll never use that as my reference. That will give me my hypotenuse here. This pi over 2 can be a reference. This 0 can be a reference. And the side lengths, those are both 1 because they are actually just glued together. And this is non-existent, so 0, because the sides are glued together. And here I can use pi over 2 as a reference angle, or I can use the 0 as the reference angle. So I have 5 special angles here. Now all of these angles can be applied in different quadrants, like all of the triangles, all of the trig ratios, I can be in various quadrants. So I'm going to fill in this radian wheel one special angle at a time. So first of all, here is 0 degrees. Top here would be 90, but in radians, that's pi over 2, half a pi, 0.5 pi. Then we have 180, which is just pi, so 1 pi. And then we have 270, which is 3 pi over 2, or 1.5 pi. And then a full rotation is 2 pi. Next, I'll do my 30-degree angles. So that is pi over 6. Now, if my alpha is pi over 6 here, and quadrant 2, pi over 6 is here. When I read my angle, it's always from the initial arm, which is on the positive x-axis, and it loops around to your terminal arm. So if I wanted this angle here, and I know this little portion is pi over 6, last year we would have done 180 subtract that alpha, that related acute angle. But this year we're dealing with radians, so pi minus pi over 6. And when I do pi minus pi over 6, and I get my common denominator, that's 5 pi over 6. When I get into quadrant 3, now I'm surpassing 180 or pi, and then I just have my related acute angle to add on. So that would be pi plus pi over 6, which gives us 7 pi over 6. And finally, in quadrant 4, I almost do a full rotation minus that little alpha. And a full rotation is 2 pi. 2 pi minus pi over 6 is 11 pi over 6. And those are the 3 angles in quadrants 2, 3, 4 that are related to our pi over 6 as our alpha, as that related acute angle. And you'll notice that all of the denominators are 6. So if you see an angle in radians, something pi over 6, that alpha will be pi over 6. You'll know which triangle to look at right away. Now let's go and do our 45. So pi over 4. In quadrant 2, we're doing pi subtract pi over 4. In quadrant 3, we're adding on the pi, so 5 pi over 4. And in quadrant 4, 2 pi minus pi over 4, so 7 pi over 4. So now if you ever see something pi over 4, the triangle you're looking at is that isosceles special triangle. Finally, our pi over 3, which is our 60 reference angle. In quadrant 2, pi minus pi over 3 is 2 pi over 3. In quadrant 3, we're doing pi plus pi over 3, which is 4 pi over 3. And finally, 2 pi subtract pi over 3, 5 pi over 3. So again, if you see something pi over 3, you know that you're looking at the pi over 3 as your reference angle in the equilateral triangle. Similar skill as in grade 11, except in grade 11, you are doing 180 subtract alpha, 180 plus alpha, 360 subtract alpha. Now we're just using pi and 2 pi instead. So let's move on to a skill from last year, which is simplifying trig ratios using your special triangles. So we're going to find the exact value of sine 5 pi over 4. Lucky for me, I see that denominator of 4, and I know right away that my alpha is pi over 4. I'm looking at the isosceles triangle. I also know that sine from SOHCAHTOA is opposite over hypotenuse. So when I look at that triangle, I'll take my opposite and my hypotenuse. My only question now is, will this ratio be positive or negative? And for that, I'm going to need my cast rule. So remember, you write cast starting in quadrant 4 and then go counterclockwise. 5 pi over 4 is in quadrant 3. And in quadrant 3, sine is negative. So we're going to have negative for our ratio. And then opposite to pi over 4 is 1. And our hypotenuse is root 2. So negative 1 over root 2. And we know we cannot end a fraction with a radical in the denominator. So we have to multiply top and bottom by root 2 to get to negative root 2 over 2. Now, how did I know that my angle was in quadrant 3? If you know your fractions, 5/4, take a look at your Cartesian grid, you can identify your quadrant like that. But I'm going to take a look at my radian wheel here. And if you use your x and y axis as a reference, this is 0 pi's, this is half a pi, or 0.5 pi's. This is 1 pi, this is 1.5 pi, and then we get back to 2 pi. When you get your angle 5 pi over 4, take 5 over 4, and if you're not comfortable with the fraction, think of it as a decimal. Go to your calculator, 5 divided by 4, it's 1.25. And then I'm just comparing 0, 0.5, 1, and 1.5. So that 1.25 fits perfectly between 1 pi and 1.5 pi. So I'm in quadrant 3. So let's go to the next one. we have secant of 5 pi over 3. Let's just talk about our quadrants first. 5 over 3 is 1.6 repeated. That belongs nicely between 1.5 and 2. So we're in quadrant 4 for this one. So I'll make a note of that. We're in quadrant 4. That's Coase's quadrant. But we're given secant, so there's a few things we need to consider here. Secant is the reciprocal of cos. Cos is adjacent over hypotenuse. So secant is going to be the reciprocal of that, so hypotenuse over adjacent. Now what's my alpha? Well, I look at my denominator and it's 3, so pi over 3. I go to pi over 3, my hypotenuse directly across from the right angle is 2, and adjacent to pi over 3 is 1. So we're going to have 2 over 1. And why is it positive? Because we're in Coase's quadrant and secant is the reciprocal of cos. So that one is done. The final one, we have 2 trig ratios we have to figure out and then just simplify this expression. So I'm going to start with tan 5 pi over 6. Well, for this, alpha is pi over 6 because of that denominator. 5 pi over 6, 5 over 6 is close to 1. It's 0 point something greater than 0.5. So I'm in quadrant 2. That's sine's quadrant. So we're going to be negative in there because we're finding the tan ratio. So now I'm going to look at pi over 6 and I want opposite over adjacent. So opposite to pi over 6 is 1 and adjacent is root 3 and it's going to be negative. So negative 1 over root 3, and if we clean that up, negative root 3 over 3. That's our first ratio. Next, we're going to look at the cosecant of pi over 2. Now, ignore the 3 for now. It is not related to your ratio. It's just an operation for later on. Pi over 2 is already one of our reference angles. It's in that fake triangle right here. So all I really have to think about here is that cosecant is the reciprocal of sine. Sine is opposite over hypotenuse. So cosecant is going to be hypotenuse over opposite. So I'm going to go to my pi over 2 triangle. The hypotenuse is across from the labeled right angle, which is 1. And opposite to pi over 2 is also 1. So that is just going to be 1 over 1. And here we are. And now we can finish with our simplifying. So I'm going to take my fractions and go to my expression. So I need to write my tan 5 pi over 6 ratio, which is negative root 3 over 3. I need to add it to triple cosecant pi over 2, which was equal to 1. And now I just need to clean this up. Get a common denominator, unite the fractions. So 3 times 1 is 3. The common denominator is going to be 3. So I'm going to have negative root 3 plus 9 over 3 because I multiplied that 3 over 1 by 3 to get 9 over 3. And here we are, our final expression, simplified. And that's simplifying trig ratios. So you need to know your alpha. You need to know your quadrant to know if you're positive or negative there. And you need to know how to draw your special triangles so you can apply that SOHCAHTOA. The opposite of simplifying is being given the ratio and you need to find the angle. So let's take a look at that. I have cos theta equals root 3 over 2. Well, first of all, I'm given cos and I'm given a positive ratio. So I'm going to go to my cast rule and ask myself, where is cos positive? Well, everyone's positive in quadrant 1, and cos specifically is positive in quadrant 4. Now I just need to figure out my alpha. So I need my adjacent to be root 3 and my hypotenuse to be 2. So I'm going to look at my special triangles and I see a root 3 here, and I see my hypotenuse of 2 here, I just have to ask myself, who is adjacent? Is root 3 adjacent to pi over 6 or pi over 3? And the answer is pi over 6 because root 3 is right beside it. So that is going to be our alpha, pi over 6. And now we can apply our classic modifications. In quadrant 1, theta is just going to be your pi over 6. But in quadrant 4, we're wrapping around, almost hitting 2 pi, but not quite there. So we're going to do 2 pi subtract pi over 6. If you get yourself a common denominator, that's 12 pi over 6. Subtract pi over 6, and you get 11 pi over 6. And those are your 2 answers. Let's try the next one. We have cotangent. Well, cotangent is just the reciprocal of tan. So you have 2 options here. You can either just look at the ratio as it is and think of cotangent as adjacent over opposite, or you can just take a reciprocal of your cotangent ratio and then forget it was ever a reciprocal to begin with. And that's what I'm going to do. Tan theta equals, I'll keep my negative, I'll flip my fraction, so it's 3 over root 3. Now when I see 3 and root 3 looks good to me. It's part of my special triangles, but the 3 isn't. So I'm just going to try to fix this problem. I'm going to multiply top and bottom by root 3 and see if that helps me out. Okay, and now the 3's cancel out and I'm left with this fraction, root 3 over 1. So I'm going to take a look at my special triangles, and I want my opposite to be root 3 and my adjacent to be 1. Root 3, 1, here they are. Root 3 has to be opposite, so pi over 3 is the winner, because across from pi over 3 is root 3. So alpha is pi over 3. Now we can go back to our cast rule. I was given a negative ratio, and we're talking about tan. Tan is negative in sine's quadrant and cos's quadrant. So in quadrant 2, this is the angle we want, and remember, pi over 3 is here, glued to your x-axis. So in quadrant 2, we're doing pi minus pi over 3. Pi is just pi over 3. So when we subtract them, 2 pi over 3. In quadrant 4, we're wrapping all the way around, except that pi over 3 is in our way. So we're doing 2 pi, subtract pi over 3. 2 pi is just 6 pi over 3 when we get the common denominator. So there we are. Last one. Sine theta equals negative 1. Well, I see a negative, so I'm thinking about my quadrants, but I also see just a simple 1. So when I look at my quadrants here, I want opposite to be 1 and hypotenuse to be 1, because we can just put the 1 over 1, and that's making me think of my fake triangle here. So if I look at my fake triangle, the hypotenuse is 1 here, and if I want this to be opposite, pi over 2 would be my winner. So alpha is pi over 2. Now in terms of my quadrants, I want sine to be negative, so that's going to be in tan's quadrant and cos's quadrant. So in quadrant 3, we're doing pi plus pi over 2, which is 3 pi over 2. And in quadrant 4, we're going to do 2 pi minus pi over 2, which is actually also 3 pi over 2. So we actually get the exact same angle, which means there's only one solution for this within the domain of 0 to 2 pi. And there we have it. solving trig equations in radians, solving for those angles as radians instead of degrees. Exact same steps, just different mode for your angles. Okay. Next, we're going to state an equivalent expression in terms of the related acute angle. This is an exercise in the cast rule, so positive, negatives, and knowing the related acute angle. So when I see tan 7 pi over 6, I see that over 6, so I know alpha is pi over 6. What this question is asking me, write an equivalent expression that's also about pi over 6 and tan. And the only real question here is tan 7 pi over 6 equal to tan pi over 6 or negative tan pi over 6? And the cast rule is going to tell me that. So 7 pi over 6 is just greater than 1 pi, so we're going to be in tan's quadrant. Well, if we're in tan's quadrant and we're dealing with a tan ratio here, we're a positive, which means tan 7 pi over 6 is equivalent to whatever tan pi over 6 is equal to, because these are both positive ratios. Let's look at the next one. We have sine 5 pi over 3. Well, alpha, of course, is pi over 3. And 5 over 3 is 1.6 repeated. We're in quadrant 4 here. That's cos's quadrant. So 5 pi over 3 is a negative ratio compared to sine pi over 3. So we make that statement. Take your sine pi over 3 ratio, make it negative, and that is going to be equal to what sine 5 pi over 3 is. For the last one, feel free to pause the video and try it out and then come back to check your work. But your alpha is pi over 4. 3/4 is 0.75. That's going to be in quadrant 2, because quadrant 2 is between 0.5 and 1 pi. And that's sine's quadrant, but we're given cos. So cos 3 pi over 4 is equivalent to the negative version of cos pi over 4. And that's it. In our next question, we're going to determine the 3 primary trig ratios for the angle negative 2 pi over 3. A diagram would be a great starting point. We already know what angle we're dealing with in terms of the related acute one, because we see that over 3, but we should get a diagram to figure out our quadrants, especially because our angle is negative. So I'm going to rewrite my grid here going in the negative direction. This is 0. This is negative pi over 2. This is negative pi, negative 3 pi over 2, and negative 2 pi if I'm going in that negative direction. So if I'm given negative 2/3, 2/3 being 0.6 repeated, I know I'm going to be between negative 1/2 and negative 1. So my angle is here in tan's quadrant. So when I write my 3 ratios, I expect my tan one to be positive, the rest to be negative. So here is negative 2 pi over 3. And my alpha is right in here, and alpha is pi over 3. So I'm going to look at my equilateral triangle to set up my ratios. Now I'm just going to draw that triangle right here so I don't have to flip back and forth. And there's pi over 3, that 60-degree angle. So now, when I do sine of negative 2 pi over 3, I'm going to use pi over 3 as my reference. Opposite, adjacent, hypotenuse. Opposite is root 3. Hypotenuse is 2. But I know this angle is in quadrant 3, and sine is negative there. So I'll make that change. Cos of negative 2 pi over 3. Adjacent is 1. Hypotenuse is 2. Again, we're negative, because only tan will be positive. tan of negative 2 pi over 3. The angle can be negative. It's the ratio that's going to be positive. That's opposite over adjacent, which is root 3 over 1. I'm just going to write it as positive root 3. And those are my primary trig ratios. Here we got to deal with a negative angle. We used the special triangle related to pi over 3 and did our traditional SOHCAHTOA. The terminal arm of angle theta in standard position passes through the point negative 2, 8. I'm going to ignore the trig ratio part as it is very repetitive to SOHCAHTOA and what we've been doing. And I'm just going to focus on solving for the angle, specifically when we don't have special angles. So our point is negative 2, 8, and we're just going to solve for theta within one cycle from 0 to 2 pi. And we're going to round to the nearest hundredth. First thing, if you're given a coordinate, plot that coordinate. So let's say negative 2 is roughly here, 8 is up here. Here's my point. Here's my terminal arm. My initial arm, I know, is on the positive x-axis. This is angle theta. I'm in sine's quadrant. If I were to do my ratios, sine would be positive, the rest would be negative. But I'm going to draw a triangle here. And in this triangle, the base is negative 2, and the vertical is positive 8. Can I solve for my hypotenuse? Of course I can. I can do a quick Pythagorean theorem and find it, but I really don't need my hypotenuse. If my alpha is here, here's opposite and adjacent, I can set up a tan ratio. Tan theta equals opposite 8 over adjacent negative 2. Now I'm going to calculate what alpha is. And remember, when we find alpha, we take the inverse function, so in this case tan inverse, of the positive ratio, because the related acute angle is an acute angle, which is less than 90 degrees, and all of our angles less than 90 degrees are in quadrant 1. And what's so special about quadrant 1? All of the ratios are positive. So if I want to find an acute angle, I need to use a positive ratio like it would be in quadrant 1. And make sure your calculator is in radians or you will be wrong. So I get approximately 1.33 radians for alpha. Now because I'm in quadrant 2, my actual theta will be pi subtract 1.33. And I just use my answer button on my calculator, pi minus answer. I kept all of my decimals and I got approximately 1.82 radians. And that is theta. Now, you might wonder, well, if tan was negative, why don't we also look at a quadrant 4 angle? But because we were given a point, this point only belongs in quadrant 2. I only have one option for theta. In our final example, we will do a little word problem using special angles, radians, and SOHCAHTOA. Two men are on opposite sides of a cliff which is 80 meters high. I'm going to start my diagram already. Two men, one's here, and there's a cliff. And that cliff is 80 meters high. They observe the angles of elevation to the top of the cliff to be pi over 6 and pi over 3 respectively. So one of them looks up and their angle of elevation is pi over 6. The other looks up and their angle of elevation is pi over 3. Draw a diagram, which we did, and find the distance between the two men. So our end goal is this, but I have two separate right triangles, so I need to solve for this space and this space individually. When I'm solving for x, I'm going to use pi over 6 as my reference, which means 80 meters is opposite, x is adjacent, and this useless side is hypotenuse. The hypotenuse is useless because I don't care about it and I don't have its length. So I need to use opposite and adjacent, which means I am using tan. So tan of my angle, tan pi over 6, equals opposite 80 over adjacent x. Now I'm not going to my calculator here because I know what tan pi over 6 is. I can draw my quick triangle, pi over 3, pi over 6, 2, 1, root 3. From the pi over 6, opposite over adjacent for tan is 1 over root 3. So 1 over root 3 equals 80 over x. I was my calculator. I don't need it. I drew my special triangle. And now we can cross multiply. 1 times x is x, and 80 times root 3. There's the first distance. I'm going to do the same thing for my other triangle. But now I'm using pi over 3. The 80 meters is still opposite. The y is adjacent. The hypotenuse is useless again. So once again, I'm using tan. So tan pi over 3 equals opposite 80 over adjacent y. And now, when I look at pi over 3, opposite is root 3 and adjacent is 1. So root 3 over 1 equals 80 over y, and we can cross multiply. Root 3 times y equals 1 times 80. This time we're not so lucky. We do need to divide out that root 3 so that we get y equals 80 over root 3. But we know this is not an acceptable end to our fraction. We should multiply top and bottom by root 3. And here is our second distance. And now we can add these values up. 80 root 3 plus 80 root 3 over 3. I would like this unified into one fraction, so let's get a common denominator. 80 times 3 is 240 root 3 plus 80 root 3 all over 3, which is 320 root 3 over 3 meters. So a little bit of SOHCAHTOA, a little bit of cross multiplying. Get your ratios from those special triangles. And now we can write a quick therefore statement. Therefore, the men are 320 root 3 over 3 meters apart. And there we go. All of the grade 11 trig skills, but this time using radians.